Hello all, and welcome to section 6.1, the last chapter of exam 2 material. Congratulations, you've made it. In this chapter, we're going to look at energy of molecules as well as some mechanism related topics. But we're going to start by looking at enthalpy, um, or the measure of heat exchanged in some chemical process. You might have learned about this in general chemistry, or perhaps even earlier, because enthalpy is one of the ways that we can first describe energy that's happening in chemical reactions and bond breaking and formations. Let's focus a little bit on the bond breaking part of enthalpy. So with bond breaking, we have two ways for a bond to be broken. One is called homolytic bond cleavage, and that's where both atoms receive an electron. So here you have a bond. Let's say it's between this X and Y atom. And in breaking this bond, you have one single barbed arrow going to one atom and the other going to the other atom. This tells you that one electron, which is represented by the half of an arrow, goes to one atom, like this, and the other electron goes to the other atom. Let's try on the other side. Here we are. These are called radicals. A single unpaired electron on an atom like this that's generated from a homolytic bond cleavage. This is called a radical atom, and radicals are very reactive in chemistry and can form bonds very easily with other atoms because that single electron really wants to be paired up with another. The other way that we can look at bond breaking is from heterolytic cleavage, where one atom receives both electrons and the other atom receives none. So in this case, our XY bond here, we're going to break it. And when we do that, a double-headed arrow is going to deliver both electrons to the X atom here. X and Y, if you remember, stand for whatever atoms we're talking about. That's a convenient way to be able to vary atoms without talking about anything in specifics. Okay, so these are the types of bond cleavage that we can have, bond breaking events. But typically, whenever we look at the energy that comes from breaking a bond, we typically look at what's called the bond dissociation energy, which is the energy required to break a bond homolytically. It's a little easier to break bonds homolytically, a little more reliable. So measuring the bond dissociation energies this way was the most expedient for past researchers. In your book, in table 6.1, there's a whole table of bond dissociation energies that might be helpful to know, or at least have a look at, and see how much energy is in certain bonds. Like for instance, if we were to look at the energy in a hydrogen-hydrogen bond, this is the most simple molecule. The energy there is equal to 435 kilojoules per mole. It's something that we talked about in one of the first lectures of this class, but we didn't really talk anymore about enthalpy specifically. This 431 or 435 kilojoules per mole is compared with the hydrogen CH3 bond, which also has 435 kilojoules per mole. There's plenty of other values in that table as well. So you're welcome to have a look. And if you need specific numbers for a problem, a table like this will be given to you. Okay, so then most reactions don't just break one bond like this. Most reactions break multiple. And so then we end up getting what's called a heat of reaction, which is the total change in the enthalpy of a reaction. So this means that you could look up the bond dissociation energies and find the heat of a reaction for a certain reaction, such as, so let's move these. There we are. Okay, if you have a reaction like this, you're taking H2 hydrogen and you are going to add this methyl iodide compound and react them to get CH4 plus HI. You can find the total bond dissociation energies for all of them. So we just said this was 435 kilojoules per mole, as was this one. So then we really just need to look up the HI and CH3I. So HI has an energy of 297 and CH3I of 234. Okay. So now we just need the total across the bond. So we add positives to the energies here because it takes energy to break these bonds. And we add negatives to the energies in the product side because we get energy from breaking those bonds. The 435s in each case cancel out. So you're left with plus 234 minus 297. That gives you negative 63 kilojoules per mole. Negative means that we have an exothermic reaction, and that energy is given to the surroundings in the form of heat during the course of this reaction. And positive delta H, had we got that, because this is a delta H value here, change in enthalpy, the positive delta H would have told us that it's an endothermic reaction and that energy was taken from the surroundings, meaning that as the reaction goes on, it gets colder. Exothermic reactions get warmer as the reaction goes on because of the energy given to the system, and endothermic reactions get colder. And you can actually make charts showing each of these. So for exothermic, let's say this is the enthalpy of the system. Whoops. This is the enthalpy, H, and it's increasing as you go up, remember? And this is the reaction on the x-axis. So if we have our reactants here, an exothermic reaction, we will lose enthalpy overall, meaning the energy is lower for the products So the energy will end up lower on the y-axis. That should be products here. And we can draw an energy diagram showing this happen. We'll get into what these things are in an energy diagram later, but we can show the negative delta H here. And the same thing for endothermic. We can make a chart with delta H here going up. This should just be H, not delta H. Then the reaction on the bottom. We have the reactants again, but this time the products are higher in energy than the reactants. And because of that, we need energy going in, positive delta H. Endothermic reaction. Okay, we'll talk more about these later on in the chapter, and we'll talk more about energy of systems in general. So this has been section 6.1.